Hi everyone, welcome back. In this video, we're going to talk about the system design of the price drop tracker, something like camel.com, a service that would scrape external websites for the products and pricing, and then provide a service to the users where a user would be able to subscribe for a specific product and be notified if the price for this product drops to the specific level. In this video, we're going to start from the high level and then go deeper and deeper in the implementation and go all the way to the database schema. We're going to talk about the service design, the database design, the schema that we would have for products, how we would send notifications, be alerted about the price drop, etc. With this, let's get to the video. We're going to start with a very high-level overview of our system and all the components. So as you can see on this diagram, starting from left to right, on the left, we have a client that sends requests to our service that is called C2E service or camel.com. What our service and system allows clients to do is first be able to search for a specific product that we would then parse and retrieve from Amazon Marketplace. At the same time, users would be able to subscribe for a specific product and be notified if the price drops on that product. So here we have a C3 service in the middle, and then it's surrounded by two API gateways. One is for the clients to be able to connect to our system, and the other one is for the vendor to be able to retrieve products from external systems. In our case, it can be Amazon, but it can be any other external marketplace. We'll have, for instance, Amazon service, so we'll be able to scrape data from Amazon Marketplace and product database, import all those products into our system, and then provide our clients ability to search across those products and be able to set up alerts for the specific product and price. Now let's add more details into our system. And as you can see on this diagram, our system would consist of three main services. It would have a search service that would allow our clients to search the products on our website instead of the Amazon and be able to set price alerts. Then we would have a product service that would be responsible for maintaining and updating a list of products that we scraped from external websites like Amazon. And the third one would be a product price timeline. This is the service that would keep track of the price changes for the specific products and be able to serve them to the user. So when I open a page, for instance, I can see the specific product price timeline and when the price changed, how often it changes, and what the ranges are. These are three main endpoints that we are going to support. At the same time, if we look at the right side of the diagram, we have a vendor API gateway that is responsible for pulling data from external websites, in our case, Amazon, and first be able to propagate the search requests to the Amazon in case we can't find those products into our own system. Also be able to scrape the product database using the product advertising service on Amazon, where we would be able to send requests for a specific list of products and then be able to get responses from the Amazon about the details and product description and pricing of those products. The way Amazon does it is that instead of direct API requests to the product advertising service, it does this through the queue, where the customers, like our system, for instance, would send requests to the SQS queue, and then from there, those requests would be consumed in a proper time and fulfilled by the Amazon product advertising service, and the results would be returned to our system either through the webhook or through a different SQS queue. So all the product scraping would be done asynchronously. We would just send messages in that queue. Those messages would be processed by the Amazon service, and the responses would be returned in the different queue perhaps or a webhook. Based on this design, we're going to go deeper into two subsystems. The first one would be the one that would scrape all the data from the external system and make sure that data doesn't become stale, or when it does, it gets updated. And the second subsystem would be the one that would use the scraped product data and allow users to create alerts for a specific product price, perhaps multiple products, and choose a channel by which they would want to be notified when the price changes. Let's look at the first subsystem that would be responsible for scraping data from the external marketplaces. As you can see, if that Amazon component remained the same, we would use exactly the same method of communication with Amazon as we discussed before through the SQS queue. In our system, it would have multiple services. The first one would be a data scraper, and this is the service that would communicate with the SQS queue and send data about the products that need to be scraped. Once we retrieve the information about these products from the Amazon, the data scraper would store them into our product database that would be implemented as a SQL database. And then from here, we have two things. First, we would have some sort of database triggers that would, on every single write to our SQL database, that would trigger an event. And that event would go to our historical pricing database that would be implemented like a Cassandra and maintain the price timeline for every single product. The database trigger would likely be implemented using some sort of queue like Kafka. So every single change of price in our product database would trigger an event that would asynchronously be propagated to our historical pricing database implemented by Cassandra. And later on, this database would be serving the price timeline data to our customer. At the same time, we would have a stale price tracker. And this is the service that would periodically scan or run a query on our product database, which is a SQL database. Using that query, you would retrieve a list of products that are perhaps stale. Let's say the price was not updated for a day or 2 days. We would retrieve all the products that have that old price information, and we would send them all the way to Kafka. And from there, the data scraper would listen to all the events in our Kafka queue and consume them and send the messages about every single product to the Amazon SQS service. And from here, we receive response from the Amazon SQS service and update our product database. But looking at the system, there are multiple issues that might happen that we want to have protection for. The first one, when stale price tracker scans the products and retrieves a list of the stale pricing, let's say the pricing that is older than 1 day or 2 days, and all those requests are sent to Kafka for future processing, we would have multiple instances of the stale price tracker. So we need to keep track of what products were already sent to Kafka, just so we don't send the same products over and over again. Just because if we have, let's say, 5 stale price trackers, then we would be executing 5 SQL queries and we would select the same products. So we would send to Kafka 5 messages for the same product. So we want some sort of locking mechanism here. And the way we can do it is by using a simple database lock. What I mean by that is that when we retrieve the product from the product database, we should have a field called status or something that would say whether the data is being scraped or the scrape is completed. As you can see here, our database schema would look something like this. We would have a product ID, timestamp, last price, status, and then description of the product, make the product data. So the status would be changed every time we retrieve a product for the scraping. And then once we receive data from Amazon about this specific product, we would change the status back to completed. This way, multiple stale price trackers would know that these specific products, even though the price is stale, but they are already in process. So walking through the whole workflow one more time, our stale price trackers, we would have multiple instances. They would be running just a range query on our SQL database, checking for the stale price and the status not scraped. And then all the data would be sent to Kafka queue. That operation is reliable once Kafka acknowledged the message. And from there, the data scraper would receive that message and send it to SQS service. Once those requests are fulfilled, we receive the data back to the data scraper, and then the data scraper would store the new data about the product into our database. We would update the timestamp of the last scrape. We would update the status as it's completed now. And if the price changed, we would also update the price. If the price is updated, we would have a database trigger on that column, and that update would trigger an event that would take this record and send it to our historical pricing database and store it there. Since we are dealing with probably millions of products here, let's talk about how they would partition the data. From the SQL database, we would just have a product ID as a primary key. It's a unique ID and uniquely would identify our data. We'd probably have indices on the status, perhaps, because it's easy to cache, and we would be retrieving a lot of it, while stale price tracker would use that field to filter to data. And on the Cassandra side, since we'll be storing the historical data, it means that every single product would have multiple price changes over time. The obvious choice here is to have a partition key as a product ID, because we want all the price changes for the specific product to be located on the same node. So if we were talking about the primary key for Cassandra, then the partition key would be the product ID, and then the clustering key, there are multiple options here. The first one, we perhaps might be using the timestamp, because if we use a timestamp, it means that if we want to retrieve the timeline for this specific product, then we would just sequentially scan all the records and not retrieve all the timelines, meaning that, for instance, we have a product price history for the last 2 years, and I want to retrieve that history only for the last, let's say, 6 months. If that's the case, then if we have a timestamp as the clustering key or sorting key, then I would only scan the records for the last 6 months, not all the records for the last 2 years. We also need to make sure that our primary key is unique. So whatever sorting key we choose has to be unique for that specific product. But I think in this case, product ID and timestamp would form a unique key by which we would be able to track every single price change for a specific product. All right, now let's move to the second part where we talk about how we would be able to set price alerts for the products. And as you can see on this diagram, we still have our Provigo database and historical pricing database over there, but now we add additional database trigger from our product database update to the Kafka and to a different subsystem. So every single time the price would be updated in our product database, there is one more event that would be triggered that would flow into the price drop service. And this service would be responsible for maintaining information about the product and users and all the alerts that users set for the product. We would be storing all the data in our Price Watch database. As you can see here, we also have a schema. Likely we would partition the database by the product ID, because we would have multiple alerts for the same product. So if we partition it by the product ID, then we'd be able to retrieve all of those alerts in one query. The Price Watch database would likely be represented as a Cassandra as well, just because we can use a really good partitioning scheme where the product ID would be the partition key, and then all the user IDs would be the sorting or clustering key. This way, if we want to retrieve all the alerts for the specific product, we would be able to do it in one request. But another good option here would also to have a price and user ID as the clustering key. This way, it would be easier for us to select users that set alerts for the specific price. So the workflow would be like this. We would have a price update for the specific product. We would store that price update in our product database. Then we would have a database trigger that would send that update to our price drop service. And then we would query the Price Watch database for that specific product and price and see what users created alert for that specific price drop. We would get a list of users. For every single user and product, we would create a separate message, and that message would be sent to Kafka queue. And then for every single message and notification would be sent through the different channel, whether it's email or browser notification or any other channel. In this subsystem, the price drop service is the key service because first, it allows users to create alerts for the specific product and price. It also receives updates about any product price changes and then checks that update against the Price Watch database. And then once we check the database and we retrieve a list of users, then potentially needs to be notified about the price update. Then we would create a message for every single user, send all those messages to our Kafka queue, and then from there we have a separate subsystem that would be called notification system, the system that would consume messages from the Kafka queue and send them through the appropriate channels. Here we would have likely a notification database as well that would be storing all the notifications that were sent to the users. At the same time, this database can be used as a locking mechanism to make sure that we can guarantee executive one delivery, meaning that we would have likely dozens of notification services because we would have a lot of different updates. And those notification services, once they consume the message, they store it in the database. And now if they fail before sending that message, we would be able to recover that message and send it over. At the same time, if some other service consumes the same message, we would check the database and find that that notification was already processed. So instead of processing the duplicate, we would just send the same notification to the user through the email or any other channel. So we would use notification database pretty much as a locking mechanism for dozens and dozens of notification service instances. And the second complex part here is our price watch database that in our case, I think it makes sense to represent it as a NoSQL Cassandra database, as we spoke before. The clustering here is important here because we want to minimize amount of records that we retrieve for the specific partition IG. If we use it inefficiently, then for every single price change of a product, we would need to retrieve all the alerts for all the users and then scan them in memory to retrieve those that set the price threshold is above or below the specific number. And this might be not efficient. Ideal case scenario here, we want to reduce the amount of records that we retrieve for the specific product ID. Maybe we can have a price and then user UUID as a clustering key. The records would be sorted by price, so we can perhaps do a range query on the price that is sorted and retrieve only those users that are below the specific price and limit the amount of users that we would need to retrieve. Because we would have alerts, for instance, if the product costs $20, we would have alert for, let's say, $19, $18, $17, $16, $15, and all the way down. And we don't want to retrieve all of those records. If the price went down to from $20 to, let's say, $18, we only want to retrieve users that had alerts between $18 and $20, and not all the users that had alerts for 17, 16, 15, and so on. So this is the challenge here. And I think the solution would be a really good one if we can just use a price and user ID for a clustering key. This way, we can use a binary search on the price, retrieve only user IDs that had alerts for the price range between, let's say, $18 and $20 if the price dropped from 20 to 18. Well, I hope my reasoning on how to choose a primary key in our case for the price watch database was clear. I have a few more videos on the NoSQL database implementation like Cassandra and how primary and clustering key work together. Feel free to check them out over here. If you want to learn more about the system design, feel free to check out my system design course that covers a lot of deep dive concepts, database schemas, APIs, and other advanced concepts. But on this note, if you found this very useful, make sure you like and subscribe, and I'll see you in the next one. Bye.